So I wanted to go over this paper that I wrote. It's called an inverse calculus for the odd layer of the Collatz map. So some keywords here: inverse calculus, meaning that the calculus traverses the Collatz map backwards. So from, say, 1 to 5 to 53 or whatever. Odd layer because we're only really dealing with the odd numbers. And of course, this is about Collatz. So there's an abstract there. I won't really read through that, or the table of contents, the appendices. Okay, so the Collatz conjecture asserts that the dynamics of the 3x plus 1 map on positive integers eventually reaches the cycle 1, 4, 2, 1. Or if we're just talking about odd numbers, it would be the 1 to 1. In this paper, we focus on the odd layer of the dynamics governed by the accelerated map. Uy is equal to 3y plus 1 over the two-adic valuation over 2 raised to the two-adic valuation of 3y plus 1, where this here, v2, is the two-adic valuation of n. Our approach develops a finite state, word-based framework for the inverse of this map by establishing a unified table of inverse operations called rows and a calculus of their composition, words. We transform the problem of reachability, meaning does the Collatz map reach every odd integer, into a deterministic procedure of solving linear congruences. Our framework rests on 3 novel components: a unified inverse table that generates certified pre-images, ux prime equals x. So in other words, we generate x prime, which is a pre-image of x, right? So if you perform the operation on x prime, you get x, since x is a pre-image. A column lift parameter called p, or you could just remember it as a lift parameter, that scales the two-adic slope while preserving modular routing, and explicit steering gadgets that manipulate the affine parameters of a word to ensure two-adic congruences are always solvable. So I'm not going to go to relation to prior techniques. However, this paper will be available for you to download. The link is in the description, so should you want to, you can do that. Okay, let's go through the notation and indices. We enumerate the ambient assumptions and notions used throughout. All variables are integers unless noted. We work exclusively on the odd layer. Inputs x are always positive odd integers. So the accelerated odd map, we just discussed it, you've just discussed it, where that denotes the two-adic valuation of n. Since 3y plus 1 is always even for odd y, uy returns an odd integer. Furthermore, for any odd y 3x plus 1 equals 4 mod 6. Yeah, dividing by powers of 2, which are congruent to 2 and 4 mod 6, yields an output uy congruent to either 1 or 5 modulo 6. Thus, the residue class 3 mod 6 never appears in the image of u. Right, so we call these the ghost inverses, even though they can be generated as inverses, but we do not use them in this system. So, families and indices. We classify odd integers x not equal to 3 mod 6, basically odd integer that's not divisible by 3, into two families. E, when x is congruent to 1 mod 6, and O, when x is congruent to 5 mod 6. To enable a finite state calculus, we decompose x into 3 hierarchical indices. So the coarse index is R, which is the floor of x over 6, R. The router, J, it's used to determine the next table row, and J is equal to R mod 3. So it's this mod 3, and so it is always any of 0, 1, or 2. And then the internal index M is equal to the floor of x over 18. That's what M is. From these, x can be uniquely reconstructed as x equals 18m plus 6j plus P6. So P6, you will call it delta, where you could say P6 or delta is either 1 or 5, and it is determined by Sx. So if the number is congruent to 1 mod 5, then P6 would be 1. If it's 5 mod 6, then, sorry, if it's 1 mod 6, P6 will be 1. If it's 5 mod 6, then P6 will be 5. So the CRT tag and reindexing, I didn't mean to obscure that. So to simplify the arithmetic of families and indices, we introduce the CRT tag T of x. So the CRT tag for odd x, the quantity t is equal to x minus 1 over 2, is an integer. The map x to t is a bijection between odd integers, x greater than or equal to 1, and non-negative integers t greater than or equal to 0. The tag T linearizes the family and index calculations, avoiding nested flaws in many proofs. Now, I also want to mention that we had said here that that 3y plus 1 is congruent to 4 mod 6. So you can write 3y plus 1, an even number, as 6t plus 4, and that t is the same as this t here, as the t in this CRT tag. So CRT stands for Chinese remainder theorem, and so that's really how we started using this. It's very important when it comes to the calculation for drift, which we'll come to later on. So here's a corollary, indices from tag. The indices Sx, J, and M are determined by T modulo 3 and 9. So X mod 6 is equal to 2 times T mod 3 plus 1. So M is equal to the floor of T over 9, and J is equal to the floor of T over 3 mod 3. Specifically, if T is congruent to 0 mod 3, then X is in E. If T is congruent to 2 mod 3, then X is in O. And the case T is congruent to 1 mod 3 corresponds to T congruent to 3 mod 6, which is excluded from the odd layer. So this is the move alphabet. We define a set of tokens, a set called A of these tokens. So capital psi, small omega, and capital omega, representing the valid transitions between families. So psi is of type E, maps family E to E. Small psi maps family E to O. Small omega maps family O to E. And big omega maps family O to O. So what you'll notice is that the capital letters map family to itself, so E to E, and big omega O to O. And the small letters map a change in family. So for psi, it's E to O, and for omega, it's O to E. So a sequence of these tokens is called a word, W, typically W. So there's a table here summarizing all that notation. I think we know them all. Well, X is an odd integer, T is the tag. We haven't come across this. M, well, M is T, the floor of T over 9, or it's also the floor of X over 18. J, S of X is X mod 6, the parity family, either 1 or 5. P is that column lift. Alpha, we'll find out what this is. So we use the symbol sigma for a two-adic valuation exponent. Its precise meaning, e.g., sigma is this two-adic valuation of AW, or sigma is a two-adic valuation of 3x prime plus 1, or sigma equals alpha plus 6p will be specified locally when used. Okay, so this is the important part, the unified inverse table. To unify all Collatz inverse orbits, we parameterize every possible step using a fixed set of row parameters, alpha, beta, c, and delta, and the dynamic column lift p, which is an integer greater than or equal to 0. This allows us to treat the inverse map as a table lookup determined solely by the indices S of X and J. So S of X meaning either E or O, and J meaning any of 0, 1, and 2. So let's look at the parameter table. So table 2 lists the 12 canonical rows derived from the constraints above. The type indicates the transition from input family to output family, e.g. EO means input E and output O. And here's the table. Here we have the symbols for each row. So remember we said here that well, these symbols here, right, so they're represented in the table, but now with a 0 for whether j is 0. But remember psi 0, 1, 2 for whether j is 0, 1 or 2. Small omega 0, 1, 2. Small psi 0, 1, 2. Big omega 0, 1, 2. And the type. Now the parameters alpha, beta, c, and delta. Right, so it said in the introduction here, a fixed set of row parameters, alpha, beta, c, and delta. So alpha, beta, c, and delta. So some of the things you'll notice is that, for example, c is -2 when the first letter of the type, when the last letter of the type is E. Now I don't want to obscure much, so I'll just erase this here. When the last letter of the type is E, and it's -8 when the last letter of the type is O. Delta is 1 when the last letter of the type is E, and it's 5 when the last letter of the type is O. These seem arbitrary, but they're not. Yeah, alpha and beta, but you can see the kind of uniformity in C and delta. The rest are as they are here. Okay, and these are fixed regardless of which inverse you're looking at. So typically the way you'd use this table is if you have a number, some random odd number, you would first take that number and find out whether it is 1 or 5 mod 6. If it is 3 mod 6, it's not included. We call those ghosts. If it is 1 mod 6, well then it belongs to E. So it's some E. Then you'd find J. So you find J by taking that number, the floor of that number over 6, and then take that mod 3. Then you'd find J, and you'd be able to classify that number in this table. Then you'd note the parameters alpha, beta, c, and delta for that number. Well, c and delta are fairly fixed depending on what number you find. It's really alpha and beta that you're looking at. And then you would slot it into this equation. So this is the unified p-lifted form. This here, the unified p-lifted form. Okay, so, and it's this equation here. So f of pm, or you'd also have to work out m for your number. M for your number is the floor of that number over 18. Okay, I don't want to obscure this, so I'll just... So this is the equation in which all these parameters kind of fit. You can see where alpha is, you can see where beta is, you can see where c is, This is P here. P is that's why we call it a column lift. Sometimes it's just called a lift because it's just 2 raised to 6p, 64 raised to p. Otherwise, as I said, I don't want to mark it up too much. And then the output for your number would be 6 times what the output from this plus delta, whatever you had here. Right? Okay, but let's read through. To reach arbitrarily high powers of 2, we extend the base table with a column lift parameter p greater than or equal to 0. Well, p is this value here in the equation. This parameter scales the 2-adic slope by 2 raised to 6p. Yes, so this is clear. While preserving the routing logic. For any row in table 2, define the lifted transform FPM, defined as so 9m times 2 raised to alpha, alpha is this column, plus beta, so and bracket that out, times 64 raised to p plus c all over 9. Then x prime, the inverse, is equal to 6 times all this plus delta. So here's integrality, a remark. Since 64 is congruent to 1 mod 9, we have, so if you extend this out, work this out, you have beta times 64 raised to p. You'd also have 9m and then 2 raised to alpha plus 6p, right? Because this is 2 raised to 6p. Beta times 64 raised to p plus c is congruent to beta plus c mod 9. Since beta plus c is divisible by 9 for all valid rows, FPM is always an integer. So this value is always an integer. Yeah. Okay. All right. So the base p equals 0 table. So if you took this expression here and set p to 0, you'd get 64 to 0 raised to 0 is 1. So that's the base table, the base case. At p equals 0, the formula simplifies to the affine forms shown in table 3. These are the fundamental building blocks of the inverse calculus. So let's just look at that table first before we tackle this section. So here is after working it all out. So remember, x prime is 6f0m plus delta. So you can slot in all the constants from the previous table, the parameter table, and work out, for example, that for E0, x prime is 24m plus 1. For E1, x prime is 96m plus 37, and so on. Right? So this is called, so it's called straight substitution because you're just substituting stuff. alpha, C, beta. M is the only thing that you need to that kind of changes depending on your value for x. Well, so does, but we know delta. We know all these C and delta because we know the output type for each row in this table. Okay, so row correctness and drift. Let's look at that. So having defined the unified parameter table and the lifted transform, lifted because of P, transform, we now verify two fundamental properties. One is correctness and the other is linearity. So correctness, every step x to x prime produced by the table is a valid inverse of the accelerated Collatz map U. Linearity, the change in the CRT tag, the drift, is a linear function of the cost index R. Okay, let's verify those two. So I'd shown you this table before. So let's look at the forward identity. So we first proved that the row design constraints derived in section 3 guarantee the forward identity. 3x prime plus 1 equals 2 raised to sigma x for all p greater than or equal to 0, where sigma equals alpha plus 6p. Right, so let's do this lemma, row correctness. Fix any admissible row with parameters alpha, beta, c, and delta, and a column lift p greater than or equal to 0. Let x be 18m plus 6j plus delta 6 be an admissible input. Let x prime be equal to 6 times fpm plus delta. Be the value generated by the unified table. Then 3x prime plus 1 is equal to 2 raised to alpha plus 6p times x. Right, so this is the inverse, the forward direction. Our inverse table takes x to x prime. Now we're taking x prime back. Consequently, the two-adic valuation of 3x prime plus 1 is equal to alpha plus 6p, and the Collatz function on x prime yields x. So substitute the definition of x prime and fpm. So we have 3x prime plus 1 is equal to 3 times 6 times the function fpm plus delta, then plus 1, because we have plus 1 on that side, plus 1. So we can simplify some. We could say 3 times 6, 18, and we're dividing by 9 here, so we could put 2 here. And then we have this, all of this, the numerator here, 9m times 2 raised to alpha plus beta, and that's in brackets, times 64 raised to p plus c, And then remember we are multiplying by 3 out here, so this becomes 3 delta, and then plus 1. Expanding terms, we get the same 3x plus 1, but now we're multiplying through by 2, so 18m 2 raised to alpha, and we're also multiplying through on this side. So we get, so that was 18, and then we also get 64p from this factor, so 64p, and then 2 times beta times 64p gives us this. Then 2 times c as well, so we have 2 times c here. 3 times delta remains the same, plus 1 remains the same, and we bracket this off in this way. Okay, so the claim is 2c plus 3 delta plus 1 equals 0. So let's verify this. We could go back to the table and we see c is negative 1, negative 2 when delta is 1. So let's check. So c is negative 2 when delta is 1. So we are going to do 2 times negative 2 is negative 4, plus 3 times delta, delta is 1, so that's just 3. So negative 4 plus 3 plus 1 equals 0. On the other hand, c is negative 8 when delta is 5. So let's look at this. So 2 times negative 8, that's negative 16. 3 times 5, that's 15, plus 1 is 16, so that's 0. Negative 16 plus 16 equals 0. So this is true, that 2c plus 3 delta plus 1 equals 0, which we have here. 2c plus 3 delta plus 1. So we can delete this part. What we're left with then is 3x plus 1, which is this side of the equation, equals 18m times 2 raised to 6p is the same as 2 raised to alpha times 64 raised to p, because 64 is 2 raised to 6. So 64 raised to p is 2 raised to 6p. So we may write 18m times 2 raised to alpha plus 6p, and this term 2 times beta times 64 raised to p, we may write 2 raised to 6p, is this term. We determine the value of beta by matching the residue part of the target odd integer. Write the target as x equals 18m plus 6j plus delta. Target meaning here x prime. The inverse row is required to satisfy 3x plus 1, 3x prime plus 1 equals 2 raised to alpha plus 6p times x. Hence, 2 raised to alpha plus 6p times x equals 2 raised to alpha times 64p. So we can factor out from here. We have the factor of 2 raised to 6p in both, and we could factor that out. Yeah, no, sorry. We're not factoring out. We're saying 2 raised to alpha plus 6p is equal to this here. So 2 raised to alpha plus 6p is equal to the same thing, and just substituting x for this value. So x is this, and we're saying 2 raised to this times x is equal to this times x, because this is x. Expanding out the right hand side gives us 18m times 2 raised to alpha 64p plus 2 raised to alpha times 6j plus delta ta 64p. So that's just split out, but it's the same factor. On the other hand, using x prime equals 6 times fpm plus delta, we have 3 x prime plus 1 is equal to 3 times 6. So substituting for x prime here, we would say 18, 3 times 6 there, 18, and 3 times delta, 3 delta, plus 1, with FPM being defined in the usual way. This becomes 3x prime plus 1 is equal to all this. I think we had already written this out earlier in this way. Okay, so we now have two expressions for 3x prime plus 1. Because this is also equal to 3x prime plus 1, and we derived this last expression here, this last term in this expression. So, and we previously had, we already verified that 2c plus 3 delta plus 1 equals 0. But so we also have this expression. So, and this expression matches, this term matches this term. So we may equate these last two as we do here. And then this gives us beta. So after some manipulation, simple manipulation, we get beta equals 2 raised to alpha minus 1 times 6j plus delta. Now we could substitute this back into our expression for 3x plus 1. So for beta, and that's removing any reference to beta. So doing so, we had come to an expression like this: 2 times beta times 64 raised to p. So now we have 2 times all this times 2 raised to 6p, and we can simplify. Multiplying 2 raised to alpha minus 1 times 2 gives us 2 raised to alpha, And then both of these terms have 2 raised to alpha plus 6p. Here 2 raised to alpha and 2 raised to 6p. So we can put 2 raised to alpha plus 6p outside of the rest of this expression. This term, excuse my loose language, and then 2 raised to alpha plus 6p, this 18m plus 6j plus delta 6 is x. We had defined that even before we started. So let x equals this. So this is x. And so we may rewrite all this, replace this with x, and that equals 3x prime plus 1. Hence, we were attempting here to prove row correctness in a long roundabout way. So we end up with what we should have if we're doing an inverse calculus, where we started with x, we get x prime, and then we go back in the forward direction. 3 times x prime plus 1 equals 2 raised to alpha plus 6p times x, which is even, and therefore the two-adic valuation of x would be alpha plus 6p. And since x is odd, the valuation is exactly alpha plus 6p. So here's an example to actually verify a row in the table. So let's take the row small omega 1 at p equals 0. So let's just let's look at it. And in fact, let's just look at the table. So this is the row here. Alpha is 1, beta is 11, c is negative 2, delta is 1. The number we're dealing with is 29, I believe. So 29 minus 5 is 24, which is divisible by 6. So already we can tell that that's an O. So 29 minus 5 is 24, which is divisible by 6. But if we divided it by 6, we would get 4. If we divided 24 by 6, we would get 4, which is 1 mod 3. And that's what gives us the 1 here. So it's O1. Now, you don't have to choose this row. There is a very, just as this O1 is just as good. You could choose this other O1 for 29 for the same value. But so let's choose this one, as in the example, and see how that works. So that's how we match 29 to one of these two rows, and then pick one, perhaps depending on the outcome you want. You want an E, you want something which would be 1 mod 6. If you wanted an O, you'd go with this second capital omega 1, which would give you an output which is 5 mod 6. But we choose this one, so let's go with it. I don't want to scale this. So let's see how that works. So x here is 29. The row gives us alpha is 1, beta is 11, c is negative 2, and delta is 1. So of course X is congruent to 5 mod 6, so family is O. And we can compute R, so we already did. R is 4. J is 4 mod 3, which is 1. Okay, so that's the correct row, or that's an admissible row. There are two options. And what is M? So M is 29 over 18 floor of that, which gives us 1. So X prime of, slot everything into F of 0, 1. We get 9, M is 1, so 9 times 1. Alpha is 1, so 2 raised to 1. Plus beta here is 11, so plus 11 minus 2. So all that comes to 9 times 1 is 9, times 2 is 18. 11 minus 2 is 9. So we have 18 plus 9 is 27. Divided by 8, so we have 18 plus 9 divided by 9 here, which is 3. So to get X prime, we take 6 times F plus, well, in this case we're going to an E, so a plus 1. So 6 times 3, 18 plus 1, 19. And so 29, the inverse of, the Collatz pre-image of 29, in the case of, in this case is just 19. So we can check. 3 times 19 plus 1 is 58. So 2 raised to alpha times X equals 2 raised to 1 times 29 is 58. So it matches. So, and similarly you could go in the backward direction, so you could go U of 19 and find that it is 29, and so verified. Okay, so completeness of the row table for non-ghost inverses. Let's prove this one. Okay, so let's go through completeness of the row table for non-ghost inverses. Remember, a ghost inverse is any inverse that is divisible by 3. So let U be the accelerated Collatz map from an odd integer greater than 0 to another odd integer greater than 0. Be the accelerated Collatz map. So U of X prime is defined as follows. It is 3x prime plus 1 over 2 raised to the 2-adic valuation of 3x prime plus 1. So that's the U of X prime. So fix an active odd target X, which is not congruent to 0 mod 3, and write X in this form. X is equal to 18m plus 6j plus delta 6. M being an integer greater than or equal to 0, j being any one of 0, 1, and 2, and delta 6 being either 1 or 5. So delta 6 is 1, corresponds to S equals E. That means X is congruent to 1 mod 6. And delta 6 equals 5 corresponds to S equals O, and X is congruent to 5 mod 6. for each integer a greater than or equal to 1 with 2 raised to a times x is congruent to 1 mod 3. So what we mean is 2 raised to a times x minus 1 over 3. Minus 1 is divisible by 3. So therefore 2 raised to a times x is congruent to 1 mod 3. Define the formal inverse. xa defined as 2 raised to a times x minus 1 over 3. I think in the previous proof we showed that, or maybe we're doing it this time, but when a is even and x is 1 mod 5, then then 2 raised to a times x is congruent to 1 mod 3. However, when a is odd and x is congruent to 5 mod 6, then 2 raised to a times x is congruent to 1 mod 3. Call xa a ghost inverse if xa is congruent to 0 mod 3. So this can happen but it means normally if xa is congruent to 0 mod 3, the Collatz tree has to terminate there because xa has no pre-images. You cannot. So that I think has been shown before. So equivalently, xa is an inactive predecessor and a non-ghost inverse otherwise, right? So here's the definition of a ghost inverse. So we call xa a ghost inverse if xa is divisible by 3, is congruent to 0 mod 3. Equivalently, xa is and so that's an odd number divisible by 3. So equivalently, xa is an inactive predecessor, right? So, and we don't consider those predecessors throughout this paper. So we're only dealing with non-ghost inverses. And so if xa is not divisible by 3, if xa is not congruent to 0 mod 3, then that's a non-ghost inverse. Then the following hold. So a number of things. 1, the unique forbidden class modulo 6. For fixed Sj among the admissible residue classes A mod 6. So this is the power of 2 here in this in this expression, this definition. So among the admissible residue classes A mod 6, A mod 6 is any of 0 to A mod 6 is any of 0, 2, and 4. Well, then S is E. S equals E. So that's the same thing I was saying earlier, that if A is even, which is when you're considering the mod 6 residues, then 0, 2, and 4 are the even ones, and then S, it has to be E, and 1, 3, and 5, well, then S is O, so of A mod 6. There is a unique residue class, A bad Sj. So one of these, among these here, one of them is bad, such that Xa is ghost if and only if A is congruent to A bad Sj. So one of these choices here always produces a an odd integer divisible by 3, so A bad mod 6. So that is the forbidden class modulo 6 of A, right? And A being the exponent here of 2. The row table selects exactly the two non-ghost classes. So let ASJ be the pair of alpha values appearing in table 2 for the two rows with key SJ. So every pair S and J. So for example, E0, there's always two such entries in the table. So let me show you the table again. So you see, like, if we had E0 is here and E0 is here, E1 is here and E1 is here, or O0 is here and O0 is also here. So we have O0 here and O0. So for that pair, so ASJ be the pair of alpha values appearing in table 2, which that's not table 2. What I showed you there is the P equals 0 table. Table 2 is the table of parameters, but the entries are the same. So you always have a pair of S and J values appearing in table 2 for the two rows with key S and J. For example, E0, the rows are capital psi 0 and small psi 0, etc. And it's always a pair like that when it comes to the symbols, because the capital symbols, I think I explained, are always same to same. So E to E, for example, O to O, and the small letter symbol is the switch, so from E to O or O to E. So so for E0, these are the two symbols. Interpreting alpha equals 6 as alpha congruent to 0 mod 6, the set ASJ is precisely the set of admissible classes excluding A bad SJ. Equivalently, for each SJ, the table contains exactly the two classes A mod 6 yielding non-ghost inverses. So I think that's kind of self-explanatory. It's just basically our parameter table includes alphas such that the bad ones are omitted. So let's look at surjectivity onto non-ghost inverses. So for every non-ghost inverse XA, that means XA is not congruent to 0 mod 3, there exists a unique choice of row in table 2 with key SJ and alpha being ASJ together with. So this expression is rewriting. So if you, for example, P equals A minus alpha over 6, if you multiplied both sides by 6, you'd get 6P equals A minus alpha. Then if you added alpha to both sides, you get alpha plus 6P equals A. So it's just another way of writing alpha plus 6P, which we know that because that is the exponent of 2 in the FPM equation. So P here is is an integer greater than or equal to 0, such that the unified lifted form, so this is the F equation, produces exactly XA. So here you see X prime equals XA, and X prime equals 6 times FPM plus delta. So this, in other words, this is every value produced by 2, which is FPM, is a non-ghost inverse. So that's basically what we're saying in this third point. Okay, so let's go through the proof. So, the proof, we use 2 elementary congruences, right? Step 1, the ghost condition is a single class A mod 6. So, by definition, if this XA is the ghost condition, that means it's congruent to 0 mod 3, which implies 2 raised to A times X minus 1 over 3 is congruent to 0 mod 3, which is XA. This implies that 2 raised to A times X is congruent to 1 mod 9. Since 2 raised to A mod 3 has a period of 6, those 6 being 2, 4, 8, 7, 5, and 1, and then repeats again, mod 9, there's 2 raised to A mod 9. The congruence 2 raised to A times X congruent to 1 mod 9 for fixed X mod 9 determines a unique residue class A mod 6. So in other words, among the 3 admissible exponent classes mod 6, A mod 6, exactly 1 produces 2 raised to A times X congruent to 1 mod 9. That 1 is the ghost class. Moreover, because X is not itself divisible by 3, so not congruent to 0 mod 3, for it to have an inverse, it cannot be congruent to 0 mod 3. So that's an additional condition. So admissibility for 2 raised to A times X congruent to 1 mod 3 forces A to have the parity dictated by X mod 3. So that means for A is even, S is equals to E, as we've discussed before, and A odd, S equals O. So if these are this is true, so this proves 1. So 1 above was the unique forbidden class among A mod 6, and here they are. This is the period of 2 raised to A mod 6. So 2, we identify the forbidden class and match the table. So from X equals 18M plus 6J plus delta 6, we have X congruent to 6J plus delta 6 mod 9, simply because the term 18M is congruent to 0 mod 9, since 18 is divisible by 9. So X is therefore congruent to 6J plus delta 6 mod 9. So a short check gives us this table. So if S is E and delta 6 is 1, X mod 9 would be for J equals, so we're starting with J here, J equals 0, so we're looking at delta 6 would be 1. For J equals 1, then we'd have 6 plus 1, 7. For J equals 2, so this will become 12 plus 1, 13 mod 9, that's 4. 4 mod 9. And A bad is in 0, 2, and 4. Right? So, the way to read this table, we already worked out what these values mean in terms of delta plus 6j, this table as well, this row as well. But the second row is what A bad should be in case, say, j equals 0. So x is 1 mod 9. A bad would have to be 0 to make 2 raised to a times x equal 1 mod 9. So here's an example. So for example, when s equals e and j equals 1, so we can see here when s is e and j is 1, we have 7, where x is congruent to 7 mod 9, and among a is any of 0, 2, and 4, this is mod 6, also mod 9, the unique solution to 2 raised to a times 7 congruent to 1 mod 9 is a equals 2, since 2 raised to 2 is congruent to 4, and 4 times 7 is congruent to 1 mod 9. 4 times 7 would be 28, which is congruent to 1 mod 9. The other entries are similar, so all these other entries show you what A bad is given these conditions. S is E, delta 6 is 1, X mod 9 is 1, 7 or 4, J in and J is 0, 1 or 2. What would A bad be in that case, right? And similarly, for the lower row, S is O, delta 6 is congruent, is equals 5, X mod 9 is congruent to these values. What would A bad be in each case? So then, now compare with table 2. Now table 2 was the table of parameters. So we had like E0, whatever, the type, then alpha, beta, C, and delta, all listed. And then for each fixed Sj, the table lists exactly the 2 alpha values, which reducing alpha equals 6 to 0 mod 6, are precisely the 2 admissible classes different from A bad in this table. So this proves 2. Right, so step 3, we're talking about surjectivity onto non-ghost inverses. So let's look at it. Surjectivity onto non-ghost inverses. So let XA be a non-ghost inverse. Then A mod 6 is admissible and not equal to A bad Sj. Hence, by 2 above, which is what we've just done, there is a unique alpha, which is 1 of A Sj with alpha congruent to A mod 6. With alpha congruent to A mod 6. So set P equals all this. So P is equal to open bracket capital A minus alpha close bracket over 6. And that value is greater than or equal to 0. Choose the corresponding row parameters, alpha, beta, C, and delta from table 2, and form x prime is equal to 6 fpm plus delta, as in the equation 2. This includes the definition of fpm and this definition of x prime. by the row correctness lemma, the lemma we just did, the previous, so before this lemma, we did a lemma called row correctness, which is here, row correctness. Let's go back to where we were. So by the row correctness lemma, 3x prime plus 1 is equal to 2 raised to alpha plus 6p times x, which is equal to 2 raised to a times x, since we define a as being alpha plus 6p. Well, anyway, even here, as we had said before, if you shuffle terms around, you see that a is equal to alpha plus 6p. So we'd multiply both sides by 6, we'd get 6p equals a minus alpha, and then we add alpha to both sides, and then we'll get alpha plus 6p equals a, right? And so we can justify 2 raised to a times x being the same as 2 raised to alpha plus 6p times x. Hence, x prime is equal to, well, the same thing, 2 raised to a times x minus 1 over 3, and which is the same as xa, which we've also seen before. Since xa was assumed non-ghost, we also have x prime is not congruent to 0 mod 3, so the produced inverse is non-ghost. Conversely, any x prime produced by 2, which was the definition of FPM and the definition of this inverse, x prime equals 6 times FPM plus delta, satisfies 3x prime plus 1 equals 2 raised to alpha plus 6p times x. So it is an inverse with exponent a equals alpha plus 6p. And by 2 above, the row table never selects the forbidden class A bad Sj. Hence, 2 raised to a times x is never congruent to 1 mod 9, and x prime is never congruent to 0 mod 3. So this completes 3 and the proof. All right. Let's go on to the drift equation, a very important equation which we'll use a lot, especially in later parts of this paper. So while the map U inverse, that is the inverse of the Collatz, what we do with the inverse calculus, appears complex on the integers, it simplifies significantly when viewed through the lens of the CRT tag, which we had introduced earlier, t of x, which is x minus 1 over 2. Right, so let's define drift. So definition: drift. For a single inverse step, x inverse x to x prime under the inverse calculus, the drift d is the change in the tag potential. So it's a change in t. And so d is defined as t of x prime minus t of x, which is equal to x prime minus x over 2. So to really get the change of the actual difference between x prime and x, you have to multiply d by 2, right? So it's that difference over 2. The drift measures the velocity of the orbit Positive drift implies the orbit moves upward, so meaning x prime is greater than x. And negative drift implies descent in the inverse direction. In fact, this is preferable in the inverse direction because when translated into the forward Collatz orbit, this becomes descent in the forward direction. However, negative drift also exists and implies x prime is less than x. And this is bad in the forward direction because it means in the forward orbit of Collatz is getting bigger and bigger, which might mean that Collatz does not converge. Anyway, we'll talk about that a lot later. So, proposition 1, the drift equation. Let x be equal to 6r plus epsilon, where epsilon is in either 1 or 5. So we're only considering odd numbers which are not divisible by 3. For any row in the unified table at column P, where this is the value of P, the drift is linear in the cos index R, right? R. So here it is. Drift, function of R and P, is equal to R times capital K plus delta epsilon, where the slope K depends on the total exponent A equals alpha plus 6p. So K is defined as 2 raised to A, where A is alpha plus 6p minus 3. And delta E is equal to delta epsilon, is equal to epsilon times 2 raised to A minus 3 minus 1 all over 6. So here's a proof of that, of this proposition, and of this drift in particular, with these values here. So from lemma 2, so lemma 2 is the row correctness lemma. So here row correctness is lemma 2, where we just showed this identity and proved it. Okay, so we're here. So the proposition, so from lemma 2, x prime is equal to 2 raised to A times x minus 1 over 3. Substitute x equals 6r plus epsilon. So this is x, right? So then manipulate this around, you'd get x prime minus x is equal to 2 raised to A times 6r plus epsilon minus 1 over 3. So right, so 2 raised to A, open bracket, 6r plus epsilon minus 1 over 3 minus, so this is x, 6r plus epsilon. So this is equal to, we start, this expression is identical to the previous one. 2 times r times 2 raised to A minus 3 plus epsilon times, open bracket, 2 raised to A minus 3, close bracket, minus 1 over 3. Right, so this is, you can derive this exactly from that, where, so if you first bring 6r plus epsilon, which, because we also have 6r plus epsilon here, and 6r is divisible by 3, so 2 raised to a times, so 2 raised to 8 times 6r, yeah, well, that's just an exercise in simplification. So dividing by 2 gives the drift. So let's look at an example. And all this can be written in terms of k and delta epsilon, or defined as they're defined here. So the drift calculation for small omega 1, assuming x is 29, so 29 minus 5 over 6 gives you, 29 minus 5 is 24, over 6 gives you 4, so r is 4, and epsilon is 5. Alpha is 1, this is read from the table, and in the p equals 0 table, so therefore a equals 1. So the taking 29 minus 1 over 2 gives us 14. That's why t of 29 is 14. 19 is the successor, so and t of 19 is 9. So the actual drift is d is 9 minus 19 is negative 5. So using the formula, k here is equal to 2 raised to 1 minus 3, which is 2 minus 3, which is negative 1. The offset, so this is epsilon here, which is, so we use k here as well, or 2 raised to a minus 3, which we know is negative 1. So we get epsilon is 5, so 5 times negative 1 is negative 5, minus 1 is negative 6, over 6 is negative 1. So then the predicted, which is d, is equal to is equal to 4 times negative 1. So 4 is so 4 here is r. Remember we calculated r equals 4 times negative 1, which is this part here, which we had calculated as k, negative 1, plus we had calculated this delta 5 as negative 1, so that's this part of the calculation. So we do that plus negative 1. So 4 times negative 1 is negative 4, plus negative 1 is negative 5, which matches the actual output that we calculated here. The thing is, with the formula, you don't really need to know the actual output, like say 9 here, the actual t of the actual output. With the formula, you only need to know a and epsilon, and epsilon comes from the actual value that you're working on. So here we're working on 29, and we know what epsilon is because 29 is congruent to 5 mod 6. So once we know 29, r and epsilon, we can apply that to the formula and come up with d. And the difference will be twice d. So the actual difference, because d is x prime minus x over 2, so the actual difference between x prime and x is 2 times d, which will, in this case, is negative 10. Then we could do 29 plus negative 10 would give us 19. Okay, let's look at a corollary here, drift bounds. So the corollary drift bounds for family E, where epsilon equals 1, the drift is non-negative. Like d is always greater than or equal to 0, with the terminal fixed point 1 to 1. Equality is only at the terminal fixed point 1 to 1, meaning d would be 0 at when you get the terminal fixed point 1 to 1. Away from this terminal fixed point, so when non-exceptional will be defined later, but you could take it as the exceptional row being O2, which is big capital omega 2. In the p equals 0 table, it has every terminal fixed point, or every non-exceptional p equals 0 row has positive inverse drift. So everything except the exceptional p equals 0 row, which is the omega 2, has positive inverse drift, meaning that there is growth in the inverse direction or descent in the forward direction. So for family O, epsilon equals 5, the drift is negative, d is less than 0, if and only if p equals 0 and the token is either small omega 1 or big omega 2. These are the exceptional, but even this small omega 1 is not, because this is an O to E transition. So it's really this where this is exceptional. This capital omega 2 is the exceptional one. On the other hand, for p greater than or equal to 1, k shows exponential. K is approximately 2 raised to 6p, making the map strongly expansive, meaning strong growth, robust growth in the inverse direction, or convergence in the forward direction. So another example here we call high lift expansiveness. Consider psi 0 at p equals 1. So this p is not 0, it's greater than 0, applied to x equals 1, right? So we get the parameters here. Alpha is 2, p is 1, A is therefore 2 plus 6, because P is 1, so it's 6P, and 6 times 1 is 6, so A is 8. So the step x equals 1 implies m equals 0, right? M is the floor of x over 18, and that's 0 in the case m is 1. So we're looking at f of 1, 0, which will give you 0 plus 2 times 64, 2 times 64, 64 because we have 64 raised to p, right? So 2 times 64 is, and then minus 2 because c is negative 2, all over 9. 64 times 2 is 128, minus 2 is 126, I believe, and then over 9, well, that gives you 14. That means x prime is 6 times 14 plus 1, which gives you 85. Well, so the drift for t equals 1, for t is for x equals 1, t of 1 is 0, because x minus 1 over 2, which is 0 over 2, which is 0. And t of 85 is 42. So therefore d is 42. The drift is 42. According to the formula, r is 0, k is 2 raised to 8 here, what we have here, minus 3, which is 253. And then for delta 1, it is 1 times 253 minus 1 over 6, which gives you 42, which matches. And that means the difference between x prime and x would be 42 times 2, which is 84, which is also true. 85 minus 1 is 84. Right, so, and then you can see just how strong the growth is in the inverse direction, as in away from 1, very strong growth. So a single step at p equals 1 multiplied the value by roughly 2 raised to 8 over 3, approximately 85. So you can see the almost exponential growth there. So we start a new section called lifted control summaries for p greater than or equal to 0. Let's dig into it. Okay, so row correctness. So we're talking about lifted control summaries for p greater than or equal to 0. Row correctness shows that each branch row admits the affine form x prime is now congruent to 6f pu, so u is kind of standing in for m here, plus delta mod mk, where it's so m sub k, capital M sub k, and I will call it mk. So mk equals 3 times 2 raised to capital K, with fpu linear in the free index u. So u or m is the free index, but this, as you can see, is a linear equation, right? Where you have so fpu is kind of the slope of, yeah, so a, you used to have a m plus a mx plus some constant c, mx plus c. So you can see here fpu here stands in for x. 6 here is m, and delta is the constant. For control arguments, it is convenient to reorganize the row parameters into derived quantities that depend on the lift level p greater than or equal to 0. So remember, P defines what table you're looking at, right? P changes the type of table that you're dealing with. Where we looked at the P equals 0 table, and that was, I think, table 3, where table 2 was just the parameters. And that table there changes depending on what P looks like, right? So here we define P as the lift level, and P can be 0 or greater, and it directly governs, so this is foreshadowing what we'll call pinning and solvability. So we're going to look at that probably in the next part of this paper. So the lifted affine form for a fixed row with parameters alpha, beta, c, and delta, define alpha p as alpha plus 6p, and kp, so kp is a constant, you could say. It is beta plus 64 raised to p plus c over 9, an integer. So this is P lift is here. This is where the P comes in, and it changes K, right? So, and using 64P equals 2 raised to 6P, the row map can be written as, so then the affine form changes. X prime is congruent to 6 times 2 raised to alpha p, which is now defined as alpha plus 6p, times u plus kp, which is all this here, plus delta mod mk. So pinning and solving depend only on the comparison of alpha p with k and the constant term kp. Router transitions are p invariant, right? Reducing, so 5 is all this here. Modulo 3 shows that the router transition triple J prime, so with R being 0, 1, and 2. Now we're going to look at R and all this in a table coming up. Depends only on the base row, not on P. Since 64 raised to P is congruent to 1 mod 3 and 6P is even, both KP mod 3 and 2 raised to alpha P mod 3 are independent of P. So table 10, this is where we're going to see what J prime and all this are, records for each input state, S and J, the two available choices for S prime. So when we put a prime on it, like X prime, J prime, S prime, we're talking about the output of the inverse calculus, right? So the output of the table, you could say, but more like the output of the inverse calculus. So the two available choices for S prime is E or S prime is O, together with the lifted parameters needed in the last step congruence. So before we look at table 10, let's just record that in practice we use table 10 to select a branch consistent with the desired output family S prime. So we're going to choose what the output looks like, and then we choose, like, if we want a particular output, then we can select that output, the output family S, and in the solving regime, solvability, and then apply the one-shot inversion procedure to compute a compatible input class, right? So we're looking at it differently now. We're looking at want to climb the Collatz tree. So where do we want to go? And then we look at what output we want and select our input class from there, right? So let's just look at table 10 before we jump into part 2, because we've just completed part 1. And part 2 regards control, right? So the control logic, which we use 2 techniques, steering, routing. Okay, let's look at table 10. This is table 5, and this is the p equals 0 classification. And what we're looking at, it's table 10 is just the general p greater than or equal to 0 output classification. So what we're looking at is the familiar rows, the familiar S and J's, and type. Alpha, beta, C, and delta are all listed here. So delta is just around here. Then as we start looking at what the outputs might look like. So S prime, this is easy to read because the type is, the input type is E, and this also tells you what the output will look like. So the output type already, the type already tells us that this is an E to E transition. So immediately S prime reads off the output transition here. So here this is the K naught for the P equals 0. K naught would change if P was greater than 0. Here kappa is a new concept, which is K naught mod 3. This tells you what J prime is based on what R is, and we'll introduce the concept of R shortly. But then you can read off what J prime is based on what you get as R. R, in fact, is M mod 3, M being, or sometimes U, but M is, when we look at the FPM, or better to say M is your input X over the flow of that X over 18. Now, you could take that M, and R is M mod 3. So it's that's what R is, and then J prime can be read off from this table here, and M prime itself would be given by, so capital M is, when you could write M as 3 capital M plus R, right? So we've already used R here, and M prime is that part of that whole, and so part of what M is. So we're writing M as 3 capital M plus R, and so M prime is given here by 2 raised to alpha, which is this alpha, times capital M plus, well, so here, in the case of where, and this varies with R. So if R was, so in the case of E naught, M prime would be given by 4 times capital M plus, if R was 0, then 0, R was 1, then 1, R was 2, then 2, etc. So this table gives you output classification, what happens down the line further up what the output looks like, and therefore you can come and feed that back into this table and get what the next output will look like. So this gives you output classification. So let's get to it. We were not here yet. We're about 10 pages back. It's the problem is that in LaTeX tables move around, so sometimes you have to search for them. So here we are. So so we just finished talking about this kind of outro to part 1, and let's start on part 2.